Section 12.3 Solubility. The term solubility describes the amount of a solute that can dissolve in a given amount of solvent. Many factors such as the type of solute, type of solvent, and temperature affect the solubility of a solute. Solubility, usually expressed in grams of solute in 100 grams of solvent, is the maximum amount of solute that dissolves at a certain temperature. If a solute really readily dissolves when added to a solvent, the solute does not contain the maximum amount of solute. We call this an unsaturated solution. A solution that contains all the solvent that it can dissolve is a saturated solution. When a solution is saturated, the rate at which the solution dissolves becomes equal to the rate at which the solid forms, a process known as recrystallization. Then there is no further change in the amount of dissolved solute in the solution. Solute plus solvent is in equilibrium with saturated solution. We can prepare a saturated solution by adding an amount of solute greater than that needed for solubility, which is saturation. Stirring the solution will dissolve the maximum amount of solute and leave the excess at the bottom of the container. Once we've saturated solution, the addition of more solute will only increase to the amount of undissolved solute. Effect of temperature on solubility. The solubility of most solids become greater as temperature increases, which means that the solution usually contains more dissolved solute at higher temperatures. A few substances show little change in solubility at high temperatures, and a few are less soluble. For example, when you add sugar to iced tea, some undissolved sugar may form at the bottom of the glass. But if you add sugar to hot tea, many teaspoons of sugar are needed before the solid sugar appears. Hot tea dissolves more sugar than it does cold because the solubility of sugar is much greater at higher temperature. When the saturated solution is carefully cooled, it might become a supersaturated solution because it contains more solute than the solubility allows. Such a solution is unstable, and if the solution is agitated or if a solute crystal is added, the excess solute will crystallize to give a saturated solution again. Conversely, the solubility of gas in water decreases as the temperature increases. At higher temperatures, more gas molecules have the energy to escape from the solution. Perhaps you have observed the bubbles escaping from a carbonated drink as it warms. At high temperatures, bottles containing carbonated solutions may burst as more gas molecules leave the solution and increase the gas pressure inside the bottle. Biologists have found that the increased temperatures in rivers and lakes cause the amount of dissolved oxygen to decrease until the warm water can no longer support a biological community. In the early morning, the surface of a lake or a pond contains cooler water, which has more dissolved oxygen and therefore more fish. Electricity generating plants are required to have their own ponds to use with their cooling towers to lessen the threat of thermal pollution to the surrounding waterways. Henry's Law. Henry's Law states that the solubility of a gas in a liquid is directly related to the pressure of that gas above the liquid. At higher pressures, more gas molecules are available to enter and dissolve in the liquid. A can of soda carbonated by using carbon dioxide gas at high pressure to increase the solubility of the carbon dioxide is the beverage. When you open the soda can at atmospheric pressure, the pressure of the carbon dioxide drops, which decreases the solubility of carbon dioxide. As a result, bubbles of carbon dioxide rapidly escape from the solution. The burst of bubbles is even more noticeable when you open a warm can of soda. Soluble and insoluble salts. In our discussion up to now, we have used ionic compounds that dissolve in water, which is known as soluble salts. However, some ionic compounds do not separate into ions in water. They are insoluble salts that remain in solids even in contact with water. Salts that are soluble in water typically contain at least one of the following ions: lithium, sodium, potassium, ammonium, nitrate, or acetate. Only a salt containing a soluble cation or an anion will dissolve in water. Salts containing chloride, bromine, and iodide are soluble unless they are combined with silver, lead, and mercury 1. Then they are insoluble. Similarly, most salts containing sulfate are soluble, but a few are insoluble, as shown in Table 12.5. Most other salts, including those containing the anions carbonate, sulfate, phosphate, and hydroxide, are insoluble. In an insoluble salt, attraction between its positive and negative ions are too strong for the polar water molecules to break. We can use the solubility rules to predict whether a salt or a solid ionic compound would be expected to dissolve in water. Figure 12.6. If a salt contains a combination of a cation and an anion that are not soluble, that salt is insoluble. For example, combinations of cadmium and sulfide, iron and sulfide, lead and sulfide, and nickel and hydroxide do not contain any soluble ions, thus they form insoluble salts. In medicine, the insoluble salt barium sulfate is used as an opaque substance to enhance x-rays of the gastrointestinal tract. Barium sulfate is so insoluble that it does not even dissolve in gastric fluids. Other barium salts cannot be used because they would dissolve in water, releasing barium, which is very poisonous.